Hello everybody, and welcome back to Z80 DWF repair videos. Here we are again with this 1982 Galaga clone bootleg board, two board set actually, arcade game that I'm preparing. This is the third video in this series, and I hope it's the last. I have enough good schematic of this CPU board, and so I'm trying to understand what's the fault, and I suggest you to review at least the second video to understand where we are at this point. The game is almost working fine, but the inputs are not working during the gameplay. Even if in service mode it appears to work everything as expected. Okay, I think I have the first clue. This time I'm positive I have a really one little clue about what's not working. Okay, the game playing alone as always, firing, and sometimes the game gets stuck in this position and no bombs reach the spaceship, so it can play forever in this situation, which is good because it allows me to have time probing around. Now the inputs are read via these two buffers, which are 10J this one and 10K this one. Lowering pin 1 means it's reading, so this is 10K, and the CPU is reading this buffer. This is 10J and it's stuck high, it's not reading, which is strange. Let's see in the schematic what I mean. So these are the buffers with the inputs connected on one side and the CPU 5 data bus on the other side. This is 10K, as somewhere it's the fire button is connected here, and this one is 10J. For sure it has right and left movements, because these two movements work in service mode, so I understood they are these two contacts, and this is not being read, but during the game you expect the CPU reads the controls. So there is something wrong finally. Okay, the two buffers are enabled by these two signals, read 2 and read 3. I call it 2 because this corresponds to 2000 hexadecimal address, and this corresponds to the 3000 decimal hexadecimal address. I mean, and it seems the CPU is not wanting to read. This gate works. There is no reads on 2000 hexadecimal during the game, or sometimes starts reading and using the inputs, but during the test mode, service mode, this is toggling, so it's reading correctly the buffer with the inputs, and there is no reason in the code. I disassembled the firmware of this CPU, and there is no reason why you should even know when it's in game or service mode, so it's really strange. It seems like this CPU is not working correctly after all. And one thing is, these two RAMs are not tested by the the main CPU, because the main CPU doesn't even know about these two RAM that are local to the CPU only. And I have an idea. I will make a new ROM for the CPU with a simple test code for all these RAMs, because there is nothing really wrong elsewhere. This address decoder is working. It seems there is nothing wrong. I'm sorry for the noise, but this is a very windy night, and in the basement there are noises with the wind. Anyway, as I was saying, I will probably make test diagnostic code into a new EPROM and try to test these two RAMs and see if they really working well. Otherwise there must be something else in this gate, but not finding anything wrong really. Well, I have to check this one, which enables the address decoder only during read and write. Let's see this one, just forgot this one. So let's understand why I think I was wrong before. As you can see, the test signal, which is the service switch, goes into this buffer, which is the one that's always being read by the slave CPU, and it goes on data bit 7 when it's read on this buffer at 3000 hexadecimal address. And this is the part of the CPU code, the one connected to that buffer taking care of the inputs. This is the interrupt routines that is called every blank period, which is every 6 times at a second. What is interesting is it reads the 3000 hexadecimal location, which is that buffer we have seen. And remember, the test switch was on bit 7. This jump JPP means it will jump to setup test if that D7 bit is 0. It means if we toggle the service switch, D7 becomes 0, reading 3000 hexadecimal. And this processor will take another path on the interrupt routine. Basically what happens in setup test, let's see if I found setup test. Yeah, it's here. Basically what happens, it clears some memory locations. Remember, memory starts at 1000 hexadecimal on this processor. So it clears some memory locations, initialize other locations to 1, like this one, initialize to B, this other one, then exit the interrupt. So what's also interesting is at the beginning of the interrupt service routine, there is this other test here. It reads the memory location at 1018, this one, decrements the content of the accumulator, reads the location into the accumulator, then decrements the accumulator. If the after decrement the accumulator is 0, it jumps to this location. I just left the label from the disassemble. 08C. 08C is this one. Basically, this one reads again U10K, the 3000, then it reads 2000, the other buffer, which is U10, yes, U10J. So it means that if the that memory location is, for example, not working correctly, it could never reach this point and read the 2000 hexadecimal buffer. Otherwise, almost all interrupt service routines it should come here and read the correct buffer. So it indeed may be a RAM problem. So let's see the code I came up to test the internal RAM of that processor. First of all, to test the complete RAM space of a processor, the code must of course not use the RAM itself. And that's quite easy, but there are three things that we don't want when we don't want to use RAM. The first thing is that we cannot call subroutines, because the return address of a subroutine is pushed into the stack, and the stack is part of the RAM. We cannot use interrupts for the same reasons, because an interrupt will save the current executing location into the stack. So first things we execute a DI instruction that disables the interrupt, masks the interrupt, and we cannot use NMI, but NMI cannot be masked because it's not maskable interrupt. And so I will need to lift the NMI pin on the processor during the test, leave out of the socket and tie to a high voltage, not to so NMI will not be triggered. That's the easier solution for this, because otherwise I would need to change the code of the master CPU not to trigger the NMIs to this one, but that would be more difficult than just lifting a pin. So let's see what I do on the test code. First of all, with these two instructions, I just make a first explosion sound, so we know the code started. Then what I do for testing the RAM is quite simple but very effective. I generated 1 kilobyte of pure random data and added to the ROM code at the end of the ROM code. And we'll copy this random data to the RAM, 1 kilobyte of random data copied to the RAM, then read what we copied again and compare with the ROM data. If they match, the RAM has no problem. If they don't match on something, I will trigger another explosion sound and raising some bits to indicate if the error happened on the low nibble of the byte or the high nibble, which is served by two different static RAM chips, as we will see in the schematics. So Z80 code on copying a block of RAM is very compact. We just put the start address on the DE register the size of the block we want to copy on the BC register. 4000 hexadecimal is exactly 1 kilobyte, and then we put in HL register the start of the memory we want to copy, which is on 0400 hexadecimal, which is after the first kilobyte of the ROM. Since the ROM is a 2732, I have actually 4 kilobytes for both the code and the random test data. So I will actually make a 3 exact loop, similar loop for testing with 3 1 kilobyte random data. The first one is generated from random generator. The second 1 kilobyte is the negated of the first random pattern that I generated. It means that the second 1 kilobyte of random data will be just the first one where every 1 bit has been turned to 0 and every 0 bit has been turned to 1. So the memory cannot really have any problem if it can hold a completely random pattern and its negated form. But since I have also more space in the ROM, I just generated a third 1 kilobyte of completely random data and used also this one. So after this LDIR is a very interesting instruction. With a single instruction we can load data from the source address, store in the destination address, increment the counters and decrement the sides, the amount of left to be copied, and repeat the same instructions until the BC register goes to 0, which is a very compact way to copy amount of memory between a source and a destination and the Z80 processor. Then we start, we stop the explosion sound. We don't need it anymore at this point, and we start checking what we copied. So this time for check I use the HL register for a source and the index X register for the HL register will hold the RAM address, and index X register holds the corresponding ROM address. I use the IX register because it permits me to make a comparison instruction directly into a memory location, which I didn't found on with other registers. But Z80 assembly is not very it's not my best one. I was very good with 6502 anyway. So we read, we make a first check cycle. We read a RAM location, we compare with the corresponding ROM location. If the compare instruction didn't give 0, it means the RAM location has a problem. So I jump to a fault code execution we'll see later. Otherwise, if it's all okay, I increment the ROM pointer, incrementing the low pointer of the RAM. I do in 2 steps, low and high, just to find when I need to stop, because when we reach 1400 in hexadecimal, that's just after the end of the RAM space, and we must stop. So we loop on CK1, which is the first check cycle, until we reach the 1400 location, of course if we don't jump to fault before. And then we jump to copy 2. I just jumped around location 38, which is here, because I wanted to put a return from interrupt on 0038, which is the location where the Z80 jumps when executing an interrupt. I know that we are not supposed to execute any interrupt, but it's good practice to leave a return from interrupt on 0038 anyway. So I just jump around this part of the memory. Then copy 2 is exact same copy and check as before, but the ROM address is now 0800, which is the second random data, which is the negated copy of the first. So as before, we check and jump on CK2 until we reach 1400, and then we jump over the NMI vector, which contains a return from NMI, just for the same reason. We should never get here, but no matter what, I just put a return from NMI in the right place. And we jump to copy 3, which yet another same chunk of code that instead uses 0C00 from ROM, which is the third completely random pattern of bytes. And we do the same copy to RAM and check again what is the RAM content. So and if nothing wrong happens, so if we never jump to the fault code, we jump forever. Forever is just almost at the beginning, but after the first explosion sound. So if nothing wrong is found on RAM, this code just executed itself forever without making any sound. Then what we do on fault. On fault we have, on the accumulator we have, when we jump on here from fault, on the accumulator we have what we read from RAM, from the RAM location that has given a problem. So I copy the byte read from RAM on the B register of the CPU, and I load into the accumulator register the corresponding ROM location, which is the correct one we should have read. Then with this instruction I will have in the accumulator the 0 bit on every bit that is correct, and 1 on every bit that was faulty. And I think I will explain why after we finish with this code. Then what I basically do is rotate the accumulator and put the bit 0 of the accumulator into the carry, which is a bit on the status of the processor that I can check and jump if it's set or not. So if the accumulator is set, it means there is a 1, and a 1 means a bit with a problem. So the first 4 bits, 1, 2, 3, and 4, are contained in the low RAM chip. So if I find a 1 in the first 4 bits rotating the accumulator into the carry, I jump to low fault. Then if the 1 is on the other 4 bits, I jump to high fault. That allows me to understand if the fault is on one chip or another. What I do in low fault is I set the bit D7 of the accumulator and the bit D4. So I write 81, and then I put this 81 into the 2000H memory location, which is mapped to an output latch on the schematic, and we'll see what happens. And for high fault, I just set always the D7, which makes the explosion sound, and D7 and what it is, 9 is D5, yes. Yeah, so this is not D4, this is D81 is D7 and D0, yeah, D7 D0. 90 is D7 and D5, D4, I mean, yes, D4, yeah, sorry. Also, I wrote that in the comment. I was not reading the comment. Okay, so I set D0 and make an explosion. If I detect a problem on the low nibble of static RAM, and I make an explosion, set D4 if an high bit is being detected wrong on the high nibble of the static RAM. So the last bit of information about the test code. In the place when we have the bad read B byte into the register B, and the good one that we wrote in register A, the accumulator. When we do the exclusive OR, it's a simple operation that gives 0 when the input bits are equal, so either 1 and 1 or 0 and 0. The output is 0 of the XOR function. When they are different, the result is 1. So let's suppose the good byte was the first one, and we read the second one, which has 2 bits flipped here in D6 and here in D0, 1, 2 and D3. We end with this pattern on the accumulator. Then we rotate right the accumulator through carry. It means on the first step it copies the bit 0 of the accumulator into the carry and shifts all the others one position. So the first rotation we had in a situation like this. This one is coming in this position, this other one is coming in this position. After a few rotations, the one goes into the carry, and we detect that with the jump and react, setting some bits and making the explosion sound. Now, the explosion sound is made by setting bit 7 on 2000H hexadecimal memory mapped latch, this one. And in the same latch we have not connected outputs. These symbols means the output is not connected anywhere. So I choose to set the D0 to indicate a low nibble problem, and D4 to indicate a high nibble problem. Either both because these 2 bits are not connected anywhere,
and because the 0 lives on the low nibble and the 4 lives on the high nibble, so it's a mnemonic thing for me. Then the mapped RAM into the processor. So we have U5D, which is connected to the low nibble of the processor, D0 to D3, and the other one is this one, which is U5C, and is connected to the high nibble of the processor. So let's burn an EEPROM with my code and see what happens.
Okay, so here is the newly programmed EEPROM. Lifted the pin 17, which is an MI, and connected to a pull-up resistor, so it will stay high. And so let's see what happens. As expected, the boot code remains stuck at the beginning of the service screen, and it's triggering continuously the explosion sound, so it means it's finding some RAM errors, hopefully if the code is correct, of course. Then if the code is correct, on EC10H, let me turn down the volume since we don't need that anymore. Okay, EC10H on pin 2, it should go high every test cycle if the low nibble RAM is bad, but it stays on 0. And pin 12 should go high and pulse as it does if the high nibble RAM is faulty, or the test is found the RAM faulty. So I guess I'm going to replace the high nibble RAM, and I hope it fixes something. Let's see. So I've socketed U5C position, replace it with a new 2114 RAM, and actually the machine is booting now. So one explosion sound, that's good. It means the test started and probably it's not finding any error anymore. So on pin 2 of 10H is this one. We should find the low constantly, yes, as before, and pin 12 also low. And if 11 is toggling as it is, yes, then it means the test is continuously running and it's not finding any error. That's good. So time to replace the original EEPROM here. Put back the NMI pin on the CPU and start the game. Ooh, credit 0. Yeah, it's working. Well, at least so far. Let's try to credit. Yep, credit 1. Okay, 2. Whoa. That's great. And start player. Yeah, it starts. So the sound ROM is still arriving to me. It has been sent thanks to Roberto for programming the new one for me, and it should be arriving in a few days. And once this is back, I can connect a normal joystick to the inputs and try to play the game. Finally, yeah. Okay, finally got replacement PROM and programmed, thanks to Roberto again. First I tried to obtain the exact Fujitsu part, which is this one, MB7052, yeah. But this one, even if advertised as an OS part, new stock, it was already programmed on a few words at the beginning, so it was not usable for this task. So since the real Fujitsu part is not very easy to find, I obtained a national 82S129, which is the national semiconductor version of this TTL PROM. Same pinout, also same programming algorithm, just a different manufacturer, and from the time where they were trying to fight over the, the part numbers of the logic chips. Anyway, let's install it in its socket, see what happens. Also wired up a quick adapter to use a normal C64 joystick, but if everything works, my plan is to build a rear cabinet for this game with a 14 inches CRT monitor, so a little bit scaled down. But so let's see if everything works at the moment. Put in test mode, so I can trigger sound with the fire, move with the joystick, trigger the sounds. So I will cycle over all sounds and see if they are correct. Of course, it would be my memory, because well, I can check on MAME emulator anyway. So we'll just check that every sound is working correct. Another thing I did is I put back the original Z80 CPU, which NEC D780 actually, but yeah, the 2.5 MHz clones according to the data sheet, and they appear to work fine, of course, since those are the CPUs that I found when I got the board. A final issue that I will try to address, it is very difficult to show it on this little camera, is that the white that I think the camera just pick up as white, but in real life this is quite pink, really evident pink, and also the spaceship is really pink on the credit. So this is a new already known issue on these bootleg boards, and it depends on the color forming resistor. These and these, also these two sets of resistors, the color output resistor of the digital to analog converter for the video signals. Someone else already figured out what are the correct values to change some of this resistor to have the correct color output, and the white to be white again and not pink. So I will quickly change the given resistors. I will link in the description the link to the web page where I found this modification. Okay, I changed the resistors. Sorry for the bars, but this game is 60 Hz and we live in a 50 Hz world. Colors are really correct now. The Galaga was deep blue before, but it should be right this light blue color. This white is really white now. The spaceship is white as well. It's not pink anymore. Credit is white again. Game Over was a blue, deep blue. Now it's the correct color. Anyway, so I consider this repair really done now. These are the new resistors that I soldered in place of the old ones, and it's been a long process, and I've been misled by several issues that were only just caused by only one RAM chip that took forever to find, and in the process I reverse engineered the board and most of the code of this CPU containing this EEPROM, the number 6. So I hope you enjoyed this long process, and thank you for watching.